Now our aim is to obtain a probability distribution function that will represent the binomial distribution close to its maximum point. So in order to achieve this task, we are going to use some of the mathematical results that we have obtained in the previous video. So I have listed them here for convenience. So let's start by considering the binomial distribution for large values of uh, elements in the ensemble. So consider the binomial distribution for large capital N. And the binomial distribution, if you remember, is combinations of capital N objects taken n at a time multiplied by p to the n q to the capital N minus n, where p represents the probability of one result, q represents the probability of the only other possible outcome of the experiments performed. And I'm going to look at the maximum point in the binomial distribution, and I'm labeling the n value which represents the maximum point n tilde. So this is the maximum point in the distribution, and we have n tilde. If you remember, the way the binomial distribution behaves is neither close to 0 or capital N. So it is far from the endpoints of the distribution, and this is going to be true as long as p is not equal to 0 and q is not equal to 0. So there is some finite probability of the two outcomes. And if you look at the variation of the binomial distribution from n to n plus 1, this should be much less than the probability for n, and that is to say that the way this distribution is behaving for the discrete n values that we consider, the variation from one point to its adjacent point in the distribution is rather small. This means that to a good approximation, we're going to have a slowly varying function. So we can say that the binomial distribution P of n can be considered as a smoothly varying function. And if the binomial distribution is a smoothly varying function, if you consider natural logarithm of the binomial distribution is also a smoothly varying function. Okay, now if I take the natural logarithm of the binomial distribution, natural logarithm of p of n, it's going to be using the properties of the logarithm, a natural logarithm of capital N factorial minus the natural logarithm of n factorial minus the natural logarithm of capital N minus n factorial plus n times the natural logarithm of p plus capital N minus n times natural logarithm of q. And furthermore, when I'm at the maximum point, n is n tilde, implies this is an extremum point. So if you take the derivative dp dn, you should be getting 0. Or if I consider the derivative of the natural logarithm of p with respect to n, that is 1 over p dp dn. If dp dn is 0, this is also going to be 0 at n equals n tilde, the maximum point of the distribution. Now, let's take a look at this derivative and set it equal to 0. So basically, I would like to find out where this maximum point is. So the derivative of the natural logarithm of p with respect to n. Now the natural logarithm of p is natural logarithm of capital N factorial. That's the first term. So d natural logarithm of capital N factorial dn. And then I have minus d natural logarithm of n factorial dn. And then I have minus the natural logarithm of capital N minus n factorial dn. And then I will have plus, since there is an n here, this derivative will give me 1, so this will be natural logarithm of p. And then I have in parentheses capital N minus n, the derivative will give me a minus 1. So minus the natural logarithm of q. So I have used the expression that I obtained for natural logarithm of p in order to write the derivative. Now I want you to recall the following relationship. The derivative of natural logarithm of n factorial with respect to n can be approximated to be natural logarithm of n for n much greater than 1. So basically, I'm going to say for this one, I can replace this derivative with natural logarithm of n to a good approximation. Now, how about this one? For this one, let me think about it for a moment. So let's have x is equal to capital N minus n. So the derivative I'm trying to find out is the natural logarithm of x factorial divided by derivative with respect to n, but n is capital N minus x. So this is d capital N minus x. So what is the differential of capital N minus x? It is dn minus dx. Since capital N is a number, it's a constant, it is 0. So this is going to be equal to minus dx. So therefore, what I'm trying to find here is minus the natural logarithm x factorial dx. And that again, because x is capital N minus n, and n is a large number, but it's still far away from capital N, I can approximately say that this is minus natural logarithm of x. What was x? Capital N minus n. So therefore, the result of this derivative is minus natural logarithm of capital N minus n. So the first term here is going to give me a 0. Why? Because this is just a constant, so this is going to be 0. So if I write this once again down here, the derivative of natural logarithm of p with respect to n is minus natural logarithm of n minus plus natural logarithm of capital N minus n plus n ln p minus ln q. This is going to be 0 when I'm at the maximum point. So basically using the property of the natural logarithm here, this is natural logarithm of capital N minus n divided by n times p over q. This is going to be 0 when n is equal to n tilde, and therefore I'm going to have n minus n tilde times p divided by n tilde q is e to the 0, that is 1. So np minus n tilde p is equal to n tilde q. Therefore, I will have np equals to n tilde parentheses p plus q. We know that p and q represent two possible outcome probabilities, so therefore they add up to 1. So I find that n tilde must be capital N times p. So this is the point, if you remember, that is actually the mean value. It is the point where I obtain a maximum in the binomial distribution. Okay, now I want to continue trying to find a probability distribution function that represents binomial distribution close to the maximum point. And in order to do that, I'm going to use a Taylor series expansion of the binomial distribution, natural logarithm of the binomial distribution at the maximum point. So let's think about Taylor series expansion of natural logarithm of p near its maximum point n equals n tilde. So I'm going to use the Taylor series expansion for this one around its maximum value and tilde. So the first term is evaluate the function at the point of interest. The second term is the derivative, first derivative with respect to n, evaluated at the maximum point n minus n tilde. And the second term is now 1 over 2 factorial second derivative of natural logarithm of p with respect to n multiplied by n minus n tilde square, and there could be higher order terms, so this is an approximation, so we will neglect those terms. And first of all, the first term here, since n equals n tilde, that's an extremum point, the first derivative must be 0. So we have two terms that can contribute. One is this term, one is this term for the easiest possible approximation I can think of. So it's an approximation for the expansion up to the second order. Now, I'm going to take the second derivative, so I need to find what is d square natural logarithm of p with respect to n. So what is this? For that, I look at the first derivative. The first derivative is here, basically. So this was the first derivative evaluated at n tilde. Okay, so let's copy the first derivative. The first derivative ln p with respect to n must be equal to natural logarithm of capital N minus n divided by n multiplied by p divided by q. Now I want to find the second derivative. So for the second derivative, ln p with respect to n, we're going to have 1 over the function that is inside. So it is nq divided by capital N minus N P multiplied by derivative of the inside. So that is natural logarithm, derivative of natural logarithm of f of x with respect to x is f prime of x divided by f of x. I'm using this derivative of the natural logarithm. So if you take the derivative of the function that is inside, from the derivative of capital N minus N, we obtain a minus 1. So we have a minus N. And then minus the derivative of the bottom, N gives me 1, capital N minus N, divided by N squared, multiplied by P over Q. Now I'm using the property of the derivative. If I'm taking the derivative of the ratio of two functions, f of x, g of x, it is f prime of x, g of x, minus g prime of x, f of x, divided by g of x squared. So I'm using this property of the ratio. And let's see what I obtain for the second derivative, ln p with respect to n. So this n and q will disappear with this n and q, and then this p will disappear with this p, and so what am I left with? Minus n minus capital N plus n divided by n times capital N minus n. So minus n and plus n will disappear. So the second derivative is going to give me minus n divided by n minus n. Now in the Taylor's expansion, Taylor series expansion, I need this to be evaluated at n tilde. So what I need is d square ln p dn squared evaluated at n equals capital NP. Remember, n tilde we found here to be capital NP. So this is minus n divided by np n minus np. So this will get rid of one of the n's here. I will be left with minus 1 over np, 1 minus p, and we all know what 1 minus p is. It is q. So minus 1 over np q is the second derivative evaluated at the extremum point. So this is going to tell me that my Taylor's expansion, Taylor series expansion, around the extremum point n equals n tilde is the first term, that is the function evaluated at n tilde, and then the second term is 1 over 2 factorial plus 1 over 2, second derivative evaluated at n tilde, 1 over npq, multiplied by n minus np, n minus n tilde squared. So therefore I can write this as, if I take the exponential of both sides, this is going to be p of n tilde, and then I will have this exponential term e to the minus 1 over 2 n minus np divided by square root npq square. And what I have obtained here has to be normalized. So, and for this to work, this has to be normalized to operate as a probability distribution function. Therefore, I need to have the integral from minus infinity to plus infinity, p of n dn, is integral from minus infinity to plus infinity, the probability evaluated at the extremum point, e to the minus 1 over 2 n minus n tilde square divided by npq dn. This has to be equal to 1. And if I call n minus n tilde y, and I also call the probability evaluated at its extremum point, or let's not do that yet. Here I'm going to have y equals n minus n tilde, and therefore n equals y plus n tilde. Therefore dn is going to be equal to dy. So I'm going to obtain here, if I also call p evaluated at n tilde p tilde integral minus infinity to plus infinity e to the minus y squared over 2npq dy. This has to be equal to 1 for it to be normalized. Okay, now let's continue with this normalization. The integral p tilde integral from minus infinity to plus infinity e to the minus y squared over 2npq dy has to be equal to 1. Now if I call this alpha, 1 over 2 npq is alpha, then basically I have here p tilde integral from minus infinity to plus infinity e to the minus alpha y squared dy. This has to be equal to 1. Now let me go back to my mathematical review. The integral from 0 to infinity, so I have this result here, e to the minus alpha x squared dx is 1 over 2 square root pi over alpha. And remember, this is a symmetric function around x equals 0, the y-axis. So this implies from symmetry that I can also calculate the integral from minus infinity to plus infinity e to the minus alpha x squared dx. That will be just square root pi over alpha. It will be twice the integral from 0 to infinity. So I use this result here. The integral from minus infinity to plus infinity e to the minus alpha y squared dy. That is p tilde square root pi over alpha. Square root pi over alpha is equal to 1. So this is going to tell me p tilde must be square root alpha over pi. So that means p tilde is equal to square root 1 over 2 pi npq. So if I substitute that result to my probability distribution function, the probability distribution function, let's remember, is given by the probability at the extremum point n tilde multiplied by this Gaussian. So it's going to be 1 over square root 2 pi npq multiplied by e to the minus n minus capital NP squared divided by 2 npq. So this is something we suggested when we considered the binomial distribution. In the continuous limit, it should be turning into what we call the Gaussian distribution. And this approximation for the probability distribution will work as long as we have a large number of elements, large n, we have a small n much greater than 1. So we should not be looking at n close to n not close to 0 or capital N. So we should be rather in the middle. Actually, better approximation when n is close to n tilde, which is capital N times p. So this is the limit in which this probability distribution function will represent the binomial distribution in the continuous limit.